And team 3 is Shelby, Hannah, Patrick, Robert, and Stacy.
Oh, are you able to see my screen now?
Yes.
Okay, perfect. So we are team 3, and our topic in general was blockchain concurrency. And so let's first introduce our group members.
I'm Shelby on the far left.
I'm Hannah.
I'm Robert.
I'm Stacy.
And I'm Patrick.
Perfect. So our general topic was concurrency in blockchain. So we were aiming to discover how to use concurrency to make blockchain more efficient. And to do this, we wanted to test the implementation of concurrent and sequential blockchains across multiple languages. So first, let's go into some background on what exactly blockchain is. So a blockchain is a chain of blocks that contains information. More formally, a blockchain is a distributed ledger that is completely open to anyone. And so once data has been recorded inside of a blockchain, it becomes very difficult to change. But why is that? First, let's go over what makes up a single block in the chain. The block's data, the hash of a block, which is hashed from the concatenation of values within the block, such as data, the previous hash, timestamp, nonce, and any other chosen values, and then the hash of the previous block. So within the components of a block, let's go into a block's data. So the data of a block depends on the type of the blockchain. For example, Bitcoin or smart contracts. For example, the data could be of a transaction, sender, receiver, amount. The hash of a block. So once a block is created, its hash is being calculated, and changing something inside of the block would cause this hash to change. This makes hashes very useful if you want to detect any changes to blocks. If the hash of the block changes, it's not the same block anymore. Another component is the hash of the previous block. So the hash of the previous block is what chains each of these blocks together. And this is one of the aspects that makes blockchain so secure. But what about the first block? As we know, the first block in a blockchain is different. It can't point to a previous block since no previous block exists. And because of this, the first block on a blockchain is called the genesis block.
All right, and now that we know what a singular block is, let's get more into the blockchain as a whole. Blockchains are often said to bring trust, security, and transparency to digital transactions. But what is it about blockchains that achieves this? We're going to be able to chain hashes with it. It has consensus algorithms and blockchain distribution. First, I'll talk about chaining hashes. So I'll do an example. Consider we have a chain of 5 blocks, each pointing to the previous block, like so. 5 points to 4, 4 points to 3, 3 points to 2, and 2 points to 1. Now let's say that block 2's data gets changed. As Hannah mentioned earlier, this means that its hash is going to change. It's going to be a different block. And since block 3 only has the original hash of block 2 stored, it can no longer point back to the block. So you have 5 to 4, 4 to 3, 3 no longer to 2, and then 1's sitting there. This means that every block after block 2 is now invalid in the blockchain. So changing a single block will make all of the following blocks invalid. Now, this alone isn't enough to prevent tampering. Modern computers can calculate hundreds of thousands of hashes per second. This means you could just tamper with a single block and very quickly recalculate all the hashes of the other blocks to keep the entire chain valid, even after tampering. To combat this, blockchains implement consensus algorithms. Most commonly in Bitcoin uses, you may have heard of one called proof of work. The intent of proof of work is to slow down the creation of new blocks. For example, requiring 10 minutes on average to calculate the proof of work per block. It just means you can't calculate all the hashes too quickly, so it makes it much harder to tamper with a block. And then lastly, one of the things that makes blockchains so secure is the distribution of them. Instead of using a central entity to manage the chain, blockchains use a peer-to-peer network, and anyone is allowed to join. When somebody joins the network, they're going to get a full copy of the blockchain. And I can't remember how big the Bitcoin blockchain is nowadays. I think it was hitting a pretty high number. But the node can use this to verify that everything is in order. So I'll give an example to make this a bit more clear. Say that somebody creates a new block. That block is going to be sent to everyone on the network who has their own copy of the entire blockchain. And each node is going to verify the block to make sure that it hasn't been tampered with. If everything checks out, each node adds this block to their own blockchain. All the nodes in a network are going to create a consensus, and they'll agree about which blocks are and aren't valid. Tampered blocks will be rejected by other nodes of the network. And then I'm going to hand it off to Robert, and he's going to talk more about what our research involves.
Okay, thank you. So once again, my name is Robert, and before we dive into specifically our research, let's talk a little bit about questions that we're trying to address here. Obviously, we want to discuss the things that we want to know about blockchain and concurrency in blockchain. We're going to talk a little bit about what we're doing, who in the team is doing what specifically, how each individual is doing that, where we are in the process, some of the stretch goals that we've thought about, which are actually things that we thought about doing maybe originally and then had to scale back a little bit and thought, well, we'd still really like to do this, but maybe it'll take a little bit more time. And then some of the results that we are expecting to see. So first and foremost, what is it that we want to know? Well, obviously, we want to know how concurrency affects a blockchain. This was kind of an interesting thing because most of us had varying degrees of experience with blockchain in general. I actually didn't have a very strong understanding of what a blockchain was. So first figuring out how it works and implementing some kind of sequential version of this was an obstacle unto itself. And then trying to figure out ways in which we could incorporate those concurrencies or parallelization was its own obstacle. But nonetheless, we want to compare these sequential and the concurrent versions of the same blockchain and see how it affects the behavior. We want to know, is there a notable difference in the speed of a blockchain between languages? So what this would mean is we would want to code the same blockchain. We want to make it as logically consistent as possible. We chose 3 different languages, which we'll discuss a little bit later. We want to implement sequential and concurrent versions among all 3 languages, making them as logically consistent as possible, and then note the changes in the efficiency for each language. So the languages that we chose. You can see that the 3 that we chose were Java, C++, and Haskell. Some of us, we all have varying degrees of experience with each of these languages, ranging from no experience at all to a lot of experience. I, for example, have no experience whatsoever in Haskell, which is why I'm not working on Haskell. So the goal is, like I said before, write the most logically consistent blockchain possible between these 3 languages. What I guess I can talk a little bit about what I mean when I say that is we want the implementation of each blockchain to be as analogous as possible, considering the constraints we have between like the differences of these 3 languages. It doesn't make much sense for us to try and compare blockchains among languages if the logic behind the implementation is completely different. So if we're not consistent about how we implement them, despite any of the nuances of the language, then it doesn't really offer us any meaningful data when we compare performance. So the idea is that first we will implement the sequential version for each language, and then we'll implement concurrency once we've perfected that. All right, so we'll talk a little bit about who is doing what. So I'm going to go ahead and pass this off to Stacy to introduce herself.
Yes, so Stacy here again. And for my research, I'm implementing the Haskell blockchain. And then I also worked on writing and editing, or I'm continuing to work on writing and editing the research paper. And then for teamwork, I help to prepare meeting agendas and lead each meeting.
I'm back. I'm Shelby. I've worked on implementing the C++ blockchain, which has been a little bit of a struggle for me because I haven't used C++ before. I've also helped in preparing this presentation. As for teamwork, I write all of our meeting write-ups for each meeting we have every Wednesday.
So it's Hannah back again. For research, I've been working on implementing our Java blockchain and preparing this presentation. And in terms of teamwork, I've been helping update our Jira, which we'll speak about later, and providing some useful tools for collaboration.
Hi, I'm Patrick. For the research, I've been implementing the C++ version for the blockchain, as well as helping to edit the research paper. And as teamwork goes, I'm helping to update the Jira and keep all our tasks up to date.
And Robert again. My research was assisting Hannah with the implementation of the Java blockchain, as well as assisting Stacy with writing and editing the research paper. And for teamwork, I generally help to lead each meeting, which is a really polite way for everyone to say I just talk a lot during those meetings. So moving on to the next slide, we'll pass everything over to Stacy.
So let's talk a little bit about our collaboration tools. In the beginning, we used Sotera to collaboratively gather and collect research into a common area where we could all access each other's notes and read each other's research. We use GitHub for version control. We have all of our sequential blockchain on our GitHub, and we are going to put our concurrent blockchain on. We also have our detailed readmes for each language and our universal test files that are text files. We use Jira for our weekly and bi-weekly sprints. We use it to track assigned tasks and our overarching goals. Discord is useful for communication, both asynchronously, and we also have our weekly meetings on Discord. Finally, for the groups that are working together on languages, we are using REPL to collaboratively code in real time. We do have some project limitations. So we are creating a specifically educational blockchain. While it does use aspects of Bitcoin, it does not follow Bitcoin exactly. So for example, we are creating a non-network blockchain. This means it's not peer-to-peer. So nodes or blocks, if you will, in our blockchain are not created on separate machines, right? Only one machine creates all of the blocks. Also, our blockchain speeds up the mining process with concurrency, and that's not really always desired. So for example, in Bitcoin, each mining of the block should take on average 10 minutes. But if we are speeding it up, then it will on average be faster than 10 minutes. So not always wanted, especially in certain aspects of the mining process in Bitcoin, but in other scenarios and in other implementations of blockchain, such as Ethereum, there are places where you can implement concurrency to speed up parts of the mining, such as in smart contracts. So for our implementation, we are using the SHA-256 hashing function for hashing our blocks and for completing the mining puzzle. Each implementation of the blockchain reads an input file, takes in each line of code from that input file, and creates a separate block for every line of code. Again, this is an educational blockchain. This is not the way Bitcoin or Ethereum or any other blockchain really does it. Our transactions, there's only one transaction per block. And then the difficulty of mining. So we define a level of difficulty in the code. And the lower the value of that difficulty, the more difficult it will be to find a hash. So far, we've completed our research. We started with some very broad questions, and after a week of research, we were able to narrow down our questions and collect more focused readings. By week 3, we were able to define our project goal, and by week 4, we began our sequential blockchains, which we had hoped to finish by week 5, but by week 5 we were not finished. So we continued and by week 6, we were finished with our sequential blockchains, and we have been preparing the midterm and the midterm report and the presentations. Next up, we're going to be working on fully testing our sequential blockchains to make sure that the implementations across each blockchain are logically consistent. And then we are going to begin creating our concurrent blockchains. And now I'm going to pass it off to Patrick. He's going to talk about some of our stretch goals.
Hi, Patrick here. So now that we've discussed what we've completed so far and what we are planning to complete by the end of our project, I'll discuss some of our stretch goals. So originally we were looking at creating a computer network to simulate our blockchains, but decided that that is pretty difficult for what we wanted to accomplish by the end of the semester. But we still thought that it was a very cool idea, so if we have time, then we will replicate all of these blockchains, or maybe just one blockchain, on a computer network to see how it performs instead of just working on a single machine. This replicating it on a network would be much more consistent to what a real blockchain, how a real blockchain works, like Bitcoin or Ethereum, and it would also provide us more opportunities to use concurrency to optimize the blockchain. We also talked about using different consensus algorithms between the blockchains, as well as adding different languages to compare to see if there are other languages, maybe Python, that would work faster. Now I'll talk about the results that we are expecting from this project. So how do we plan on measuring the results? So with each sequential blockchain and concurrent blockchain, we will be comparing the times when fed the same data, the times of execution. So we are expecting the concurrent blockchains to run more efficiently and faster than the sequential versions. And we will also like to see the comparison between the 3 different languages that we selected to implement the blockchains. The division of the work between the languages means that none of us really had a complete idea of how the language will compare to the other languages for the blockchain implementations. So we are excited to see how they compare. Also, the limitations in the blockchain's logical consistency between the languages can result in changes in speed, but not necessarily attributable to concurrency, as well as a lack of an included SHA-256 hashing function in C++ could affect how C++ runs the blockchain. And lastly, distinctions in general speeds between the languages, even with consistency issues. And our general expectations for the project, we know that concurrency should increase the speed, but like I stated before, all of our familiarity with concurrency is a deciding factor, so how we implement it within each language will also affect the execution time for each blockchain. Also, the Java virtual machine abstracts from the operating system, so it creates virtual threads instead of C++ and Haskell using lower threads. So Java might run a little bit slower because it's using higher level threads. And that's about it. So now we can have time for any questions.
Really interesting work, and also very different. So today we saw 3 very different presentations. I really enjoyed your work, hearing about your work on blockchain. I also really like the organization of your team. You have regular meetings, you split up the tasks nicely, you use collaboration tools. That's how it's done. I was very pleased to see this. But now let's hear some questions from everybody in class. We have maybe some time for 1 or 2 questions. Okay, no questions. Just a curious fact, by the way, the author of the textbook, Maurice Herlihy, He's currently working, he's on leave from his university, from Brown, and now he's at Algorand, which is like a blockchain company.
Yeah, actually, we saw in some of our research in the initial phases of the project, one of the reports that we read was co-authored by Herlihy, and it was specifically about I think utilizing STPs to better implement like smart contracts in Ethereum blockchain, and that was actually one of the things that originally we were looking at. There were some other authors that kind of ran with Herlihy's ideas, as well as some of those other papers. So there were papers that as we were researching, we saw like, oh, Herlihy and his co-authors, they had this idea, and then we could kind of see the dialogue progress in other reports as they kind of picked up from that thread, which was kind of neat. But ultimately we decided on like a proof of work style, because we thought that maybe the smart contracts would be a little bit too difficult for us as undergrads.
Yeah, it was a combination of the difficulty, and also we really wanted to try implementing a blockchain across 3 languages. And from research we did with it on Ethereum white paper, we realized that might not really be a good idea for doing with Ethereum. So we kind of tried to change the blockchain instead of changing our language goals. So that, but I do find Ethereum very interesting. It's just a little bit different of a project.
Absolutely, absolutely, I agree. And I also like your strategy of first implementing it sequentially, so you have a good understanding of what it is, and then trying to think of how you can parallelize it. So
yeah, we explain it in our research paper, but we know exactly how we're going to parallelize. So we have a very specific point in the code, actually in the mining, where we're going to parallelize for each language.
Perfect. Well, I think it's time to go for today, but thank you for the really great work and nice presentations. And I will see you again on Wednesday.
Thank you.